Hello friends, today we are going to see structure and synthesis of naphthalene. So let us go to structure and synthesis of naphthalene. A moment till the thing is full screen. Okay, it takes some time. So now let us see the unit 4 in your syllabus, that is naphthalene structure and synthesis. After naphthalene, we will be seeing phenanthrene and anthracene. Okay. So naphthalene belongs to polynuclear aromatic compounds. They are also known as polynuclear aromatic hydrocarbons, or in other words, PAH. Okay. These compounds, why are they so special? Because they contain more than one aromatic ring systems in their structure. Benzene is one aromatic ring system. These compounds contain more than one ring system. Now, depending upon the arrangement of the aromatic ring systems, the polynuclear aromatics are divided into two types. One are isolated systems, which contain multiple isolated rings. We will see them later. Second are fused systems, which contain at least two aromatic rings or more, which are fused, and the fusion is such that they share two common atoms between them. Look at naphthalene. These are the two carbon atoms which are common between them. Okay, and they are adjacent to each other. Right? So, the first among polynuclear aromatic compounds is naphthalene. Any polynuclear aromatic compound has n+1 resonating structures. Remember this, any polynuclear aromatic compounds has n+1 resonating structures where n corresponds to the number of rings. Okay. Now, naphthalene has two rings and so it has three resonating structures. Let us see how. This is the first structure that has been drawn. In the second structure, what has happened? The resonance has occurred only in one ring. So this double bond moves here. As a result, this carbon becomes pentavalent. So this double bond moves here. As a result, this carbon becomes pentavalent. And this is electron deficient. So this moves here. And this results in a structure number 2. Just have a look at structure number 2. The right hand side ring is not affected. Now in structure number 3, what happens is, see, this can move over here. As a result, this moves over here. So this carbon becomes pentavalent, this moves over here, this moves over here, and this carbon is electron deficient, and so this double bond shifts over here. As a result, the third structure is formed. And actual naphthalene is a resonance hybrid of all these three structures. Look at the three structures. Naphthalene is a resonance hybrid. Now, the next question is, which is the most stable among these resonating forms, or are they equally stable as in benzene? So, for polynuclear aromatic compounds, there is a rule called as Fry's rule. The Fry's rule states that in polynuclear aromatic compounds, the most stable form is the one in which maximum number of rings are in benzenoid structure. Now, what do you understand by benzenoid structure? 3 alternating double bonds. Okay. Now, look at this form. It has 3 alternating double bonds. Look at this structure. One ring at least has 3 alternating double bonds. But here in this structure, both the rings are 3 alternating double bonds because this double bond is common to both the rings, right? Here only one ring is in 3 alternating double bonds. Here too, one ring is in alternating double bond. So here, in the first structure, maximum number of rings, that is both rings are in benzenoid structure. I hope it is clear. This double bond is common to both the rings and therefore this ring is in benzenoid structure and this ring is also in benzenoid structure. That is not so over here or here, and so structure number 1 is the most stable structure of benzene. I hope this is clear. Then the next observation about naphthalene was, if you try to recollect benzene, benzene has all 6 bonds with a common bond length. And that is how the benzene structure was finally solved. Okay, here in naphthalene, all the bonds do not have same bond length. Okay, look at bond number 1, 2. This bond is 1.36, whereas this bond is 1.40. Okay. Now, why so? Why adjacent bonds have different wavelength, different bond lengths? Let us try to understand. I have written here the resonating structures of naphthalene. Now, when you look at the resonating structures of naphthalene, in 2/3 of the resonating structures, this double bond is a double bond form, whereas in the third structure, it is in single bond form. Okay. So, most of this has more double bond character. The bond number 1, 1, 2, let me write the numbers over here, although we have not covered numbering, but let me write here numbers. Okay. Bond between 1 and 2 in 2 structures is a double bond, and in the third structure it is a single bond. So the bond 1 2 has more double bond like character than bond 2 3. Okay, if we consider this carbon as 3, then it will be bond 2 3. So bond 2 3 has more single bond like character, and therefore bond length of bond 1 2 is 1.36 because it has more double bond like character, whereas bond length of bond 2 3, bond between 2 and 3, is 1.40 because it has more single bond like character. Okay, I hope this is clear. Now let us go to numbering of naphthalene ring. Okay, by convention, the numbering always starts in a polynuclear aromatic compound with the right-handmost ring and that too topmost carbon. Okay, the numbering starts with right-handmost ring and topmost carbon, and that is the reason why I have numbered this as number 1. Just have a look, right-hand side ring, topmost carbon. The second important rule to remember is the numbering should complete one ring before going to the second ring. Okay. So 1, 2, 3, 4, then comes 5, 6, 7, 8. Okay. But you can start with any position and still the numbering remains same. There are only 2 different positions in naphthalene, alpha and beta. Okay. Just try to understand how. You write this chloronaphthalene. You write it this way. You may call it 1-chloronaphthalene because the numbering starts from here. Because, this is 5 and so on. Okay. Now, instead, if you write this way, starting the numbering from topmost carbon is just a convention, but what is more important is the only substituent should get the lowest possible number. And therefore, if the structure is written in this way, you can start numbering from here. If this is 4, then this should be 5. You cannot go to this carbon as carbon number 5. You will take this as 5. Okay. Instead, if you are given a structure like this, still it is 1-chloro-naphthalene. Why? Because starting from the right hand ring is the convention, but substituent getting the lowest possible number is extremely important. It is not a convention. Okay. So therefore, when you have this type of structure, you start numbering from here. 1, 2, 3, 4. Then this becomes 5. Okay. If you have this structure, still it is 1-chloro-naphthalene because you can start numbering. The substituent should get the lowest possible number. I hope this is clear. Now, if there is 2-chloro-naphthalene, you just cannot start numbering from this chloro, sorry. You just cannot start numbering from this chloro. Okay, because you have to complete numbering of one ring before you go to other ring. And usually the junction carbons are not numbered. So if you start numbering from here 1, 2, 3, then you cannot go over here. It has to be continuation. One ring numbering has to be in continuation. And so you will have to start numbering from here itself 1, 2. So that you get you give the lowest possible number to the substituent bearing carbon. 3, 4, and then go to this as 5. Okay. Now instead, if you are given this structure, still the rule is same. Complete the one ring before going to another ring numbering and give lowest possible number to the substituent bearing carbon. And therefore, the numbering becomes this way. If you are given this structure, still it is 2-chloro-naphthalene because 1, 2, 3, 4. First ring is complete. Then you go to 5, 6, 7, and 8. So, there are only 2 positions of monosubstitution. You can have either 1-chloro-naphthalene or 2-chloro-naphthalene. Okay, although you may be able to write 4 structures like this for 1-chloro-naphthalene, it is the same 1-chloro-naphthalene. Okay. Now, coming to synthesis of naphthalene. Okay, naphthalene can be obtained by coal tar distillation, but naphthalene can also be prepared in the laboratory. So there are 3 methods for synthesis of naphthalene. The first method among them is by from 4-phenyl-but-1-ene or 4-phenyl-1-butene. Just see, this is phenyl 1, 2, 3, and 4. So you start numbering from here 1, 2, 3, 4. At 4 position, there is phenyl. So this is 4-phenyl-butene. Now, what is there in the structure? This structure has all the necessary carbons. Just a fusion is needed and fusion followed by an additional double bond over here. So that is achieved when 4-phenyl-1-butene is heated with red hot calcium oxide. You get naphthalene. Another way, another method of synthesis, 4-phenyl-but-3-enoic acid. Okay, this is 1, 2, 3, and 4, butenoic acid. At 4 position, there is a phenyl, and at 3 position, there is a double bond. So 4-phenyl-but-3-enoic acid. Okay. Here again, there are 4 carbons, so a ring closure is needed. H from here and OH from here goes in presence of concentrated sulfuric acid. You know, OH is not a good leaving group, but when it is reacted with H plus, it becomes a good leaving group. And so you get a carbonyl group over here. I think you have heard about the keto-enol tautomerism. A similar thing happens over here. This is the keto form, this is the enol form. Exceptional case where enol form is more stable because of the aromatization due to the enol form. And when this is distilled with zinc dust, the OH group is removed and you get naphthalene. So this is the second method. Now, the third and the last method, that is Haworth synthesis of naphthalene. This is a Friedel-Crafts reaction. Benzene can be converted to naphthalene. Just see how this is succinic anhydride. Succinic anhydride reacts with benzene in presence of AlCl3. So this is a Friedel-Crafts acylation. Now what happens during this? The carbonyl group acylation, so a carbonyl group gets attached. Then there are two CH2s and finally the COOH. Okay. Now we don't want a carbonyl group over here. We want CH2 and so it is treated with zinc amalgam HCl where Clemenson's reaction happens or Clemenson's reduction happens. This reaction is Clemenson's reduction, where a carbonyl group is converted to a CH2 group. Now, a fusion occurs just like the previous reaction. There is sulfuric acid. It converts OH to a good leaving group that leaves and a bond is formed between carbonyl carbon and the ring. Now what you need? You don't want a carbonyl carbon here. Why? You must be thinking why? Because previous example, it was okay. But in the previous example, if you see, there was a double bond over here. And so the keto-enol tautomerism could be shifted to the enol form. Here, there is no double bond. And so we once again do Clemenson's reduction. And when we do Clemenson's reduction, this gets converted to 1,2,3,4 tetrahydronaphthalene. Okay. This can be aromatized by treatment with palladium over carbon, where the hydrogen will be lost and naphthalene will be formed. Okay. So that is about synthesis of naphthalene. Now in the next lecture, we are going to see the reactions of naphthalene. So till then, bye. If you like the lecture, please subscribe to the channel and hit the like button. Thank you.